Hey folks, Ms. Gosling here. In this video, you're going to learn about absorption and emission spectra. By the end of the video, you will be able to explain and interpret absorption and emission spectra. So let's go ahead and get started by looking at the absorption and emission spectra for hydrogen. So on the top, we have our emission spectrum for hydrogen. You can see we have a red line, a blue line, a purple line, and a couple of indigo, like almost ultraviolet lines, kind of right around the edge of the visible range. In our second picture, we have the absorption spectrum, which is the first picture is all of the wavelengths of light that hydrogen can emit. And the second one is all the wavelengths of light that hydrogen can absorb. And you'll notice that the absorption and emission spectra are kind of exact opposites of one another. So every wavelength that is emitted is not absorbed. So it lines up with a black bar representing the part in the line of the absorption spectrum where we don't have any photons getting absorbed. Now, how can I see these absorption and emission spectra, you might ask? Well, it's actually a pretty simple setup. So we start out with a tube of atoms at low pressure. So you want some gas, some hydrogen gas. And what we're going to do is we're going to connect that to some sort of electrical discharge. So we have electricity running through that gas. That's going to supply energy to the gas, which is going to allow it to start emitting photons. When it does that, we're going to want to make sure that the radiation is incident on a slit in what we call our spectrometer. Then, what we'll do is we'll send that light through either a diffraction grating or a prism, and I'm going to go ahead and draw a diffraction grating because it's a little bit easier, and let it project onto a screen. And when we do that, we'll actually be able to see the emission spectrum for hydrogen, which is pretty cool. We'll be able to see those spectral lines. We can do a very similar setup to get the absorption spectrum. But for that scenario, what we're going to want to do is actually start with a white light source, like a light bulb, so that we have every available wavelength of light present. And then we'll send it through our sample. So for example, we could send it through some hydrogen gas. And then we'll again send it through a spectrometer, a diffraction grating, and project onto a screen of some kind so we can see the absorption spectrum as well. And you'll notice those black lines represent those atoms which are absorbed by hydrogen. So again, the black lines are the atoms that are absorbed by hydrogen and thus the ones that can later be emitted by hydrogen. So those lines, either of color in the emission spectrum or of darkness in the absorption spectrum, represent the wavelengths of photon, the energy level differences, therefore, within the hydrogen atom. So let's go ahead and get into some of the kind of physics of this. So within the hydrogen atom, we have a whole series of energy levels. And each of those energy levels is represented by a different photon, right? Because we have a different photon that gets emitted to go from one energy level to the other. So for our first energy state, for our first energy level, if we start at the second energy level and we go to the first energy level, what we'll start out with is we'll start with a change in energy, negative 13.6 over 1 squared plus 13.6 over 2 squared, or negative 10.2 electron volts. And what we'll see is that is going to correspond to a photon with a frequency of delta E over H, or 10.2 times 1.6 times 10 to the negative 19th, divided by 6.626 times 10 to the negative 34th, which is 2.5 times 10 to the negative 15th 2.5 times 10 to the positive 15th hertz, which is going to be in the infrared spectrum. And in fact, we'll find that every jump to the first energy level is going to be within that infrared spectrum. And we call this the Lyman series. So that the hydrogen emission and absorption spectra that we actually see are going to be those jumps to the second energy level, which is known as the Balmer series. And if you were to do those calculations, you would actually see that they are all within the visible spectrum. So that's how you get those lovely 4 lines on our emission spectrum. The final series that we're actually going to talk about is the jumps to the third energy state, which we call the Paskin series. And that is going to be in the ultraviolet spectrum. So again, when we're looking at our electron spectrum in a spectrometer, those lines that you're going to see are all going to be within the Balmer series, since that is the visible part of the spectrum. Thus, it will all be jumps to that second energy state. Now, the last thing that I'd like to mention, and I just want to point this out to you here for folks who may have forgotten from chemistry. When we're drawing our energy, our atomic levels in an atom, those energy levels, we want to make sure that our gaps between energy states decreases over time. And this is actually going to come from that 1 over n squared component of the function. So, of our energy function. So, because we're dividing by n squared versus n, we're going to see the difference between the energy level difference between higher energy levels is going to be lower than the energy level difference between 2 lower energy levels. So for example, the energy difference between n equals 5 and n equals 4 is much smaller than the difference between n equals 1 and n equals 2. So I do just want to mention that as something to keep in mind when you're drawing your atomic spectrum for an atom. Keep in mind that you should have bigger gaps that then decrease over time. So just summarizing a little bit here, the absorption spectrum for hydrogen, pictured here, represents the wavelengths of photon that electrons and hydrogen can absorb to jump to a higher wavelength. And specifically, it's the wavelengths that they absorb, that the atoms on the second energy state will absorb to jump to higher energy levels. The emission spectrum is going to be the exact opposite. So it's actually going to be the energy released when an electron goes from a higher energy state to a lower one. So for example, from n equals 3 to n equals 2. And that's going to give us that emission spectrum for hydrogen. So let's go ahead and talk takeaways. First of all, atoms can only absorb the frequencies of light that correspond to a jump in energy levels. So from, for example, n equals 3 to n equals 2, n equals 2 to n equals 3, a jump in energy levels, or n equals 1 to n equals 7, but it's going to always follow one of these specific values. And second, the absorption and emission spectra are exact opposites of one another. So the dark bands in your absorption spectrum are the light bands in your emission spectrum. And there you have it, folks. You now know about the hydrogen atom. It's your turn to solve some problems. Best of luck and happy solving.